Section 7.2, the sampling distribution of p hat. How good is the statistic p hat as an estimate of the parameter p? To find out, we asked what would happen if we took many samples. The sampling distribution of p hat answers this question. So, if we were to do this activity, you would get onto a computer and you would go to a specific website that is going to imagine a very large candy machine filled with orange, brown, and yellow candies. When you insert money, the machine dispenses a sample of candies in the activity. You will use the applet to investigate sample-to-sample variability in the proportion of orange candies dispensed by the machine. So the figure to the left shows one set of possible results from step 4, which describes how many or what proportion would be orange if we took a sample size of 25 candies and we took 400 samples. If you can tell, the distribution or the shape is roughly symmetric, it's unimodal, and it's bell-shaped. It looks like a normal curve would approximate this distribution fairly well. The mean of those 400 samples has a proportion of 0.448. This is quite close to the actual population proportion of 0.45 or 45%. So look at the spread. The standard deviation of those 400 values of p hat from these samples is 0.103. So the dot plot below is approximate sampling distribution of p hat. If we let p be 45% and take all possible sample sizes, simple random samples of n equals 25 candies from the machine, and graph the values of p hat from each sample, then we would have the actual sampling distribution of p hat. We can get an idea of its shape, center, and spread from the dot plot below. So again, this is just from our approximate sampling distribution. It is not the actual sampling distribution, since this is not all possible samples of size 25. In a similar way, we can explore sampling distribution of p hat when n, or our sample size, is 50. As the figure to the left shows, the dot plot is once again roughly symmetric, unimodal, and bell-shaped. This graph is also centered at about 45%, with our samples of size 50. However, there is much less spread in the values of p hat. The standard deviation of the figure to the left is 0.068. For the samples of size 25, it was 0.103. To repeat what we said earlier, larger samples give a sampling distribution that has a smaller spread. What if the actual proportion of orange candies in the machine was 15%? The figure to the left shows the approximate sampling distribution of p hat when we take a sample size of 25. Notice that the dot plot is slightly skewed to the right. The graph is centered close to the population parameter of p equals 15%, and the spread is similar to the standard deviation when n is 50. Our standard deviation is 0.071. If we increase the sample size to 50, now the sampling distribution of p hat shows even less variability. The standard deviation of the figure is 0.048. So note that we can't just visually compare graphs because the horizontal scales are different. So the dot plot is more symmetric than the graph when n, or our sample size, was 25 and the proportion was 15%. And once again, it is centered very close to the actual population proportion of 15%. So what we've learned so far about the sampling distribution of p hat. When we're talking about the shape, in some cases, the sampling distribution of p hat will be approximated by a normal curve. This seems to depend on both the sample size of n and the population proportion p. The center, or the mean of the distribution, is the mu of p hat, which is just going to equal our p-value. So this makes sense because the sample proportion p hat is an unbiased estimator. So what we're saying is the average of all our p hats, or average of all the sample proportions, should equal the actual proportion of the population. For the spread For a specific value of p, the standard deviation gets smaller as the sample size gets larger. But the value of our standard deviation depends on both the sample size and the population proportion. To sort out the details of shape and spread, we need to make an important connection between the sample proportion p hat and the number of successes x in the sample. In the candy machine example, we started by taking repeated simple random samples of size 25 candies from a population with a proportion of 45% of orange candies. For any such sample, we can think of each candy that comes out of the machine as a trial of this chance process. A success occurs when we get an orange candy. Let x equal the number of orange candies obtained. As long as the number of candies is in the machine is very large, x will be very close to a binomial distribution with our sample size of 25 and our proportion at 0.45. Remember, for us to be able to use this binomial distribution, our sample size must be 10% of the population or less. So the sample proportion of successes is very closely related to x. To find our p hat, we're just going to do the count of successes in our sample over the sample size, or x over n. From Chapter 6, we know that the mean and standard deviation of a binomial random variable can be found just by doing the number of our sample size times the proportion. And to find the standard deviation of x, we can just do the square root of our sample size times the probability of success times the probability of failure. Since our p hat is just x over n, we can write that as 1 over the sample size times x. We are just multiplying the random variable x by a constant of 1 over the sample size to get the random variable p hat. Recall that from Chapter 6 that multiplying by a constant multiplies both the mean and the standard deviation of the new random variable by that constant. So we know that the mean of our p hats is just going to equal 1 over n times the mean, which from Chapter 6 we know is n times p. 1 over n and n will just cancel each other out, so we're just left with that p value, which confirms what we already thought, that p hat is an unbiased estimator of p. And to find the standard deviation, remember you're just going to do 1 over n times our standard deviation for x. And our standard deviation for x is just the square root of n times the probability of success times the probability of failure. Now to get rid of that square root, we can square both sides. So we're going to end up with 1 over n squared times n times p times 1 minus p once we've gotten rid of that square root. Now, we're going to go ahead and move that n squared to the denominator, because we're just going to multiply 1 over n squared times that quantity. And then we can divide by an n on top and bottom. So this is just going to leave us with the square root of p times 1 minus p over n, or the square root of our probability of success times the probability of failure over the sample size. And we need to remember, as sample size increases, the spread will decrease. That's because our sample size is on the denominator, and so as that n value gets larger, it will make our fraction smaller. That takes care of our center and our spread, but what about the shape? Multiplying a random variable by a constant doesn't change the shape of the probability distribution. So the sampling distribution of p hat will have the same shape as the distribution of the binomial random variable x. From Chapter 6, we know whenever our sample size times the probability of success and the sample size times the probability of failure is at least 10, we know a normal distribution can be used to approximate the sampling distribution. So as long as both the sample size times the probability of success and failure are at least 10, we can use a normal distribution to approximate the shape. And since we're just multiplying for that x value by a value that is a constant to get our p hats, the p hats will also be normally distributed. So for our sampling distribution of a sample population, you need to choose a simple random sample of size n from a population that has a size large N with a population proportion of p. We're going to let p hat be the sampled proportion of successes. So the mean of our sampling distribution of the p hats will just equal the proportion for the entire population. To find the standard deviation of your sampling distribution, you're just going to do the square root of the probability of success times the probability of failure all over the sample size, as long as that 10% condition is met. So remember, you have to make sure that your sample size is less than or equal to 1/10 of the entire population. And as n increases, the sampling distribution of p hat becomes approximately normal. Before you perform normal calculations, you do need to check that the normal conditions are met. So remember, you're going to do the sample size times the probability of success and the sample size times the probability of failure, and both of those values must at least be 10 to be able to use our normal approximations. The two conditions in the preceding information are very important, that 10% condition and our normal condition. When we are sampling without replacement for a finite population, the proportion P of successes is actually changing as we select each individual. And since we're not replacing them, remember that proportion is going to change with each sample we take. But the standard deviation formula assumes that P remains constant. If we sample too large of a fraction of the population, our calculated value of the standard deviation of our P hats will be inaccurate. And we need to check that normal condition. If we assume that the sampling distribution of p hat is approximately normal when it isn't, our calculations we make using the normal distribution will be flawed. So a polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of home. What is the probability that a randomly selected sample of 1,500 students will give a result within 2% percentage points of this true value? Follow the four-step process. So remember, when you follow the four-step process, you start with your state. So you determine what question you're trying to answer. In this case, we want to find the probability that p hat falls between 0.33 and 0.37. This is 2 percentage points away from 35%. Or we're trying to find the probability that p hat falls between 33 and 37%. Next is we need to come up with a plan. For our plan, we need to check to make sure all of our conditions are met first. So we have a simple random sample of size 1,500 drawn from a population that has a proportion of 35% who attend college within 50 miles. So because we know the population proportion is 35%, it means that the mean of all of our sample proportions will also be 35%. Now, before we can find our standard deviation, we need to make sure the 10% condition is met. If we do 10 times that 1,500, it means that our population would need to at least be 15,000 people. And since there's over 1.7 million first-year college students, we have definitely met that 10% condition. So since the 10% condition is met, we can now find that standard deviation. And remember, the formula for that is the square root of the probability of success times the probability of failure all over the sample size, or the square root of 35% times 65% divided by 1,500. And we're going to get a standard deviation of 0.0123. Now, before we can do any normal calculations, we need to check the normal condition. So we do need to do our sample size times the probability of success, which will give us 525, and our sample size times the probability of failure, which gives us 975. Since both of those values are at least 10, we can use normal approximation, and it should be quite accurate. So from here, this is where we do the do part of our problem. This is where we actually find all the calculations. So the plan is just making sure we can do everything and we have all the information we need to do those calculations. So on the do, when you're doing normal approximations, you can use the z values. So we will find the z-score when p hat is 33% and when p hat is 37%. Remember, z-score is x minus mu over sigma. So for 33%, we'll do 0.33 minus 0.35 over the standard deviation of 0.0123, and we'll do the same thing for 37%. Once you get those two z values of negative 1.63 and positive 1.63, you're going to go to Table A. Remember, in Table A, it tells you the area to the left of these values. So if we have negative 1.63 and 1.63, to the left of negative 1.63 will tell me this piece. To the left of positive 1.63 will tell me this piece. So if we subtract those two areas, that will tell us the part that is in between those two values, which in this case will be 0.8968. And the last step in a 4-step problem is to conclude. So based on that, we can say about 90% of all the simple random samples of size 1500 will give a result within 2 percentage points of the true value of the population. So let's check our understanding. About 75% of young adult internet users age 18 to 29 watch online videos. Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion p hat in the sample who watched online videos. What is the mean of the sampling distribution of p hat? So if the population proportion is 75%, then the mean of our sampling distribution of p hat will also be 75%. The mean of the sampling distribution is the same as the population proportion. Find the standard deviation of the sampling distribution of p hat and check that the 10% condition is met. So if we take a simple random sample of 1,000 young adults, if we multiply that by 10, our population would have to at least be 10,000 young adults in the United States. We know that there are much more than 10,000 young adults ages 18 to 29 in the United States, so the 10% condition is met because this 1,000 young adults is definitely less than 10% of the entire population. Since it is less than the 10% rule, we can go ahead and find the standard deviation. And remember, our formula for that is the square root of the proportion of successes times the proportion of failures all over the sample size. So we can do the square root of 75% times 25% all over 1,000, and that's going to give us a standard deviation of 0.0137. Is the sampling distribution of p hat approximately normal? Check the normal condition is met. So to check the normal condition, remember you do the sample size times the probability of success, and you do the sample size times the probability of failure. And this is going to give us 750 and 250. Since both of those numbers are greater than or equal to 10, we know that the normal condition is met. If the sample size were 9,000 rather than 1,000, how would that change the sampling distribution of p hat? Remember, as the sample size gets larger, the variability of your sampling distribution gets smaller. So the standard deviation in this case would become much smaller, but the mean of our p hats or the p value would remain the same.